All right. Thank you so much, Philip and James, for being here. Go ahead and kick off your screen share. We're all excited to hear about PgCache this morning.
Thanks. While James is pulling that up, I'll uh, I'll lead us in, and so I'm the one who gets the word out about PgCache, and James is the one who builds it. So I'm gonna let him carry most of this talk. But thanks, Elizabeth. Thanks everybody, Ryan, for hosting. This is really exciting. This is the kind of the biggest, most public conversation we've had about PgCache. It's been mostly small one-on-one chats and everything up till now. But super excited to be here and present on what we're building. So we can go to the next screen, and I'll just give you a quick orientation on the structure for the talk, so you know what you're getting into or getting out of. Yeah, so we're going to start with logical replication, and I don't want to spoil James's work, but basically what we're pulling together, and jump into an overview of how we got to the PgCache idea, what we've built out so far, and where the product stands, and then we'll do a short demo, talk over that, and then a couple observations about the current state, and where we see this maybe going in the future in terms of architectural implications for how people scale Postgres. And then we'll wrap that up and get to a Q&A, which we're really excited about. It's fun to have other folks like Renee on the call, who I know hopefully will have some interesting points of view on what we've built. And we're looking forward to learning a lot from you guys as well. So I'll do, like I said, a quick overview of PgCache as a project. The goal is really just to leverage logical replication in a cache. We call it a smart read replica, because that's sort of what it ends up being, and James will describe that a little bit more. But the goal is to make it easier to run and then scale production Postgres. So again, a lot of overlap with some existing projects, but the way we approach that, I think, is a little bit different. So we're 1 year in. There's just two of us. I'm the kind of the pretty face or not so pretty face, depending on the day. And then James is the one who's really building it all. He's been in Postgres since the .com era, is how he puts it. I think just one other piece, just to help level set a little bit on where the project stands before I hand over to James. We're pre 1.0, so the product is fully armed and operational, I guess you could say. We haven't done a lot of testing on actual production data, and we're under an Elastic V2 license, so that's source available. And the reason we're doing that is because in addition to building a really great community tool that helps the Postgres ecosystem, we'd love to have a business kind of more on the enterprise end of things, and we'd like to be able to develop that before AWS decides to host it and eat our lunch. So that's what PgCache is. Where it stands, I'm going to pass it over to James, who's going to, I think, give us the meat of the talk.
Right, cool, thanks. Yeah, so we are gonna start to talk a little bit about logic replication, how I ended up at the caching idea. So kind of a very light overview of where logic replication come from. Originally had the physical replication. The Postgres folks started working on making that more flexible, more selective, enabling cross-version replication. And then kind of where we are today, the community kind of took the logic replication tools that Postgres provided, and kind of really ran with it. There's a ton of companies, and kind of taking an overview of the space. They're mainly focused on warehousing and analytics solutions. I put up a bunch of companies here. There's probably a dozen other companies and projects that could have listed. And then where I kind of arrived at, which is to try and use logical replication for caching as kind of another use case, another way of leveraging the replication stream. So the question is, how did I end up here? How did I get here? I'm going to talk about where the motivating problem I had for this, because it kind of it's helpful because it kind of illustrates kind of the relatively unusual approach I took to building the cache, which I'll talk about a bit later. But the genesis of this was when I was working at a digital asset management company, I guess probably 5 or 6 years ago. At this point, we had our assets in a CDN on the edge, distributed around the world, um, images and videos and documents. Um, and the was doing what CDNs do. They're reducing latency to the end user. Um, but since it's digital asset management, authorization, protection of the assets, making sure only people who are allowed to see a given asset was very important. And so every request to get an asset still needs to do a database call back to the origin database in New York. Um, and I guess kind of being a typical engineer, like this was felt like this could be more elegant. Like it'd be really nice if 100% of the requests could be served on the edge, with the benefit that would have for latency and the end user experience. Um, so I kind of wanted to make this happen. I was thinking at the time, there's got to be something to do it. How hard can it be just to cache the data where you need it? I spent some time looking around for a tool that could do it. I couldn't find anything. Um, and then where logic replication comes in is logic replication had just been released a couple of years ago in Postgres. And so the thought was, well, I just need the data. Here's this really convenient CDC stream that has all the events they could, keep the data up to date with. Um, how hard could it be to just kind of combine those two desires? Kind of to give away the question, it could be harder than you thought it was when you started. Um, so kind of going to move into a quick overview of PgCache, and kind of the guiding principle that was used that the cache was designed around. Um, to go through architecture ideas to try and keep this relatively simple. Um, One of the goals with building the cache is to try and make it really easy to use, to have something that just works. This is where the idea comes from of just having uh, being able to just redirect the connection string to the cache, having it speak the Postgres wire protocol, having it generally look like Postgres. If you've done developments on websites and you've ever considered caching, it's always kind of a um, engineering decision with its own trade-offs and balances, and you have to decide whether the cache, when you want to build the cache, it's worth the effort to spend the time building the cache for the payoff and the maintenance that you're going to add. And so part of the goal is, can we make that decision a little bit easier? Can we make it much more simpler to add a cache without the overhead of changing your code and updating it and figuring out how to invalidate. Um, so internally to PgCache, there's basically two pieces to it. There's a proxy that's written in Rust that handles the Postgres wire protocol. And the cache itself is in fact backed by Postgres. So there's an internal Postgres instance that's being managed by the proxy. This is definitely a bit inspired by the just use Postgres movement for everything. And then on the other end, the proxy talks to origin. It will, forward queries that it can't cache. It'll forward writes forward to origin. Things that it can cache, it'll manage the Postgres or serve them from the internal Postgres instance. And then it's also listening to the logic replication stream from origin to help maintain the cache and decide whether a query can be served or needs to be invalidated or can be updated. Um, so when I started writing the cache, I think most people are familiar with caches essentially storing results. This kind of goes back to the original problem I had where uh, calculating the authorization was not a complicated query. It was not computationally expensive. The real problem was the data just was too far away. So when I started building the cache, the principle that it's organized around is, cache the data, not the results. So cache the data, you need to compute the results, but don't store the computed results itself. Um, this ended up having some kind of interesting benefits, some drawbacks. But now, kind of a year into it, I could say that I'm kind of really happy having taken a somewhat unusual approach because I think it's paid some dividends. Uh, And again, when I started out, um, my concern was, making this very easy to use. Everyone's aware of the risks of having a replication slot. It's a very good way to take down your database if you're not careful enough. I've built into PgCache to try and make it a little bit easier on people who have to manage it. The PgCache team in itself will manage the lifetime of the slot. It'll create it if it doesn't exist already. It'll remove the slot and exit so you don't have a forgotten slot. Um, can't take care of 100% of the instances. So there are ways for PgCache to die or be killed that the slot doesn't get cleaned up. So, you still need to monitor the replication slot in your primary as I feel is probably pretty typical these days. Um, next section, I'm going to talk about some of the lessons and discoveries I had along the journey. Hopefully you find these interesting. Uh, the first one is again having to do with schema changes and logical replication stream. When I started out, I was kind of familiar with logical replication stream. If you do any research on logic replication, one of the first things you come across is, DDL is not part of the stream. Schema changes are not part of the stream. And so I was concerned that this was going to be a rather significant issue for making a cache that was kind of very low maintenance. Um, and then fairly early on, I learned that there is actually schema related information. So I'm not going to say that, schema changes are necessarily part of the stream, but there is a relation message that the stream will embed before it sends you any events related to that table. And the stream also keeps track of whether the table has changed since the last relation message it has sent you. So basically, when you receive the relation message, it's pretty straightforward. It basically contains all the columns and the column names. Um, I don't remember offhand. I don't even think it includes the data types that I have to go back to the origin to learn the data types. But it is in regards to the cache, it's actually uh, covers 90% of the problem of dealing with DDL changes. Um, there's an interesting sort of caveat about when the relation message shows up. It only shows up when there's actually a write, basically an event that it has to send for the table. So if the table is not busy, if the table is primarily just read, um, the schema can be changed, and then you might not learn about the change for, whatever, a few minutes, an hour, however long it takes for that first write to occur. I think people who run uh, logical replicas are definitely familiar with the problems this causes for a logical replica. That time gap could be, fatal. Uh, for a cache, the cache has the luxury of falling back to origin if it sees something it doesn't understand. So if you change the schema to a table and you start sending queries to the cache that use a column that the cache doesn't recognize, it's just going to pass that through to origin. And it's not going to be a failure. It's not going to be as critical as it is for an actual replica. Um, so when I first started out, I was a somewhat unreasonable hope that I could build a cache that didn't have to invalidate anything ever. Um, reality caught up with me pretty quickly in this regard. Um, there's a So for very simple single table queries, it's actually possible to always keep the necessary data up to date using what comes through the replication stream. As soon as you get to non-trivial queries, as soon as you get to joins, you run into situations where you get an insert into a table that would cause the join to pull in more rows that the cache hasn't seen yet. In that case, the query that comes invalidated and it'll be repopulated next time it gets hit. Um, I include this because I had a not great couple of weeks when I came to this realization because I, had this vision and I was like, this kind of sucks. Um, Kind of sat with it for a while, thought about it, accepted it, and then realized that uh, while a magical cache like that would be great, being able to automatically handle invalidation itself is actually very valuable. There's the well-known joke that there's two hard things in computer science, naming things and cache invalidation. So being able to take that responsibility to cache invalidation away from the developer and be able to handle it uh, cleanly without any additional work you know is useful, I hope. So um, moving farther into the development process, uh, uh, when I started, wasn't sure whether this was going to be feasible at all. Obviously, I had high hopes. Spent a lot of time building the initial version, getting kind of basic queries working, getting basic, cache hits, cache misses, population working. Um, Spent a bunch of time adding some features, and then uh, at some point realized that I had something that could work, something that was going to be pretty good, um, but nobody would care if it was not consistent. And so I ended up spending some time working on consistency. And what makes it a bit challenging is that there's two ways that data can get into the cache. The first way is when you see a query that's cacheable, and you need to populate the cache from origin. So that's one way data is getting into the cache. And the second way is obviously the logical replication stream, the CDC stream. As changes are coming in, the data needs to be updated. I've put here an example of one of the problems you could have if you don't have your consistency story correct. It's one that happens to be the first one that I really came across. Um, this case was what I called ghost rows. Basically, the cache could end up still serving a row that had been deleted from origin. The way this would happen would be essentially a race condition between population and the delete occurring or the delete appearing on the logical replication stream. Um, so essentially what happened, population could kick off, the delete could come through, and then population finishes, and it used to store into the cache what it saw when it initiated the population. Um, so the way this is set up in uh, the cache to work now is leverages the LSN, I believe the log sequence numbers that Postgres exposes. So population is tagged with, or population knows the log sequence number of when it grabbed the data. The CDC stream also has the log sequence numbers associated with it that are sent in the replication stream itself. And so the code goes through a fair bit of effort to essentially make sure that the population CD streams are synchronized based on the tagged LSNs. Um, there's definitely more detail to it than that, but that's a basic idea, is trying to keep those two streams synchronized with each other so that the data in the cache table that's being cached is consistent with what you would get from origin. Um, Sort of the last lesson I'm sharing, this was fairly early on in development. Uh, as I mentioned before, the cache has the luxury of falling back to origin when something goes wrong, when it sees something it doesn't understand. Um, the goal is to, certainly in production, to make it as robust as possible, so that if your cache, if there's something going on with your cache, that it's not taking down your whole website, that you still have the fallback to origin. Um, I'd set up my original tests were, black box tests. I had some basic queries, I had some queries. Uh, I would run it through the cache. I'd make sure the data I was getting back was correct. Um, Initially, this was fine. It was working. Go do a bunch of development, introduce a bunch of bugs into your own code. Um, and then your tests are all still passing, and you're like, oh, this is great. And then you notice something's a little weird, and you look in a little bit closer, and you realize uh, that the cache is silently erroring, and everything is getting forwarded to origin, and your tests weren't really helping you at all. Uh, so uh, if your system has a safety net, if there's a fallback path, black box testing is not going to be sufficient. You need some sort of white box testing. So this kicked off a bunch of instrumentation work in PgCache so that the test could know what was happening internally to PgCache to make sure that there was a cache hit when it's expecting there to be a cache hit, to make sure there's a cache miss when it's expecting there to be a cache miss. This also ended up kind of paying dividends later because all this instrumentation has basically turned into metrics that that are exposed through a Prometheus endpoint. Um, the next up, I'm going to switch to a demo, show you a bit of how PgCache is working. The demo is recorded. It's not a live demo. I didn't want to fat finger anything in front of you folks. But it's a video, so I'm going to switch over to the video and I'm going to kind of talk about what's happening. So, yeah. So this is what some of you who are folks were on earlier were talking about the Pagila database. If you're familiar with it, it's a sample database based on movie database. So it has actors, it has films, has a bunch of tables. We're just going to be using a few of the tables. So I describe here the actor table, a table linking actors to the films that they're in, and the film table, uh, fairly straightforward. The exact details of the columns, probably not that important. Um, I'm also going to say that the demo is probably pretty dense and it's going to move fairly quickly. So if you have questions, which I hope you guys do, please ask them at the end. Take note of them. Um, and all right, I'll keep going. So the first thing we're going to show, I can highlight stuff. There's a function, a pseudo function that the proxy looks for called PgCache explained. And that lets you pass a SQL query. You can also pass a fingerprint, and then basically will expose information internal to the cache about the query you're asking about. So we're going to use this here to show when stuff is not when things are not in the cache, and a little bit more information for when they are in the cache. So we're starting out here, very simple query against actor. We're just looking up a single row. It's not in the database yet, the data. Where did I go? Sorry, that was a little quick. So we ran the query, we got the results back. It triggered the cache population. We run explain, we can see that it's now in the cache. There's a bunch of stuff here that I'm going to get to and explain a little bit later. So we went through, there's now a query hit. I'm also going to just kind of draw your attention to the graph on the top, the two graphs on the top. The one on the left is just all the queries going through PgCache. The one on the right will be the cache hit rate. It's going to be useful for this demo because when something is served from the cache, you should see it have a little spike. If it's not served from the cache, then you won't see it. So yeah, just bringing your attention to that. So continuing on, we're going to do a little bit more complicated query, slightly more complicated, not really complicated. This one's just getting all the films that the specific actor was in. It exercises joins, illustrating that they will also work through the cache. Um, so do a little explain here, explaining a little bit of what we're seeing. This is the fingerprint that the query is associated with in the cache. And then skipping down to this line, this is showing you what the SQL is actually executed against the internal Postgres database and the associated explain plan for that SQL. And again, just showing that it comes back from the cache. At this point, we're going to start moving into exercising the writes where the logical replication comes into play and how this affects the query freshness or whether it has to be invalidated. The first update is going to be a very simple one to the last name of the actor. Since the queries don't directly depend on this field for which rows need to come back, this is something that can be kept, the queries can be kept fresh in the database. They don't have to be invalidated. So I'm going to do the update. I'm just going to show that both of the queries are still present in the cache. The next one we're going to move up to is we're going to delete the link from the actor to the first film. Oh, sorry, showing that the results are updated. So this is the select. You can see that it's coming back from the cache and that the last name was updated. Same thing for the join query. So now we're going to delete one of the links between the actor and one of the films. About this update is actually the first query isn't affected, but the join query, because we're simply removing a row, the cache is able to know that all of the necessary data to serve the query is still up to date and accurate in the cache, so it doesn't have to invalidate the query. So we're just going to show that the query is still in the cache. And that the result comes back with the film ID 1 no longer coming back as associated with the first actor. And then the next update, the last one we're doing is to insert the row back. And because when you insert a row into join, when there's a new row into the join, that may cause other parts of the join to have to pull in additional rows. We can't guarantee that those rows are already in the cache. So this actually causes the query to be invalidated, which you can see with the PgCache explain, comes back, tells you that that it can't be served, that it's invalidated. So that the cache knows about it, but it's been invalidated. And we'll go through, run the query. So let me go back a little bit. What we're going to show here, we're going to move on to some of the more additional features that were built on top of the idea of cache the data, not the results. What we're going to show now is what we called covered queries. Sometimes talk about it as subsumption. This was something that was enabled by the fact that we're caching the data. When we see a new query come in, we could basically determine by comparing the where clause for that query to the already existing queries, whether we can prove the necessary rows to answer that query are already in the database. Sorry, not already in the cache. And so we don't have to populate from origin, we could serve it directly from the cache. So for the demo, we're going to use Pretty simple queries. Sorry, that was a little fast, but basically we just selected star from the film table. So we're effectively um, loading the entire film table into the cache. So uh, if we do another query where we're just looking for a single film, the cache is able to compare this where clause with the non-existent where clause of the full table query, and it's able to know that all the rows are in the database. I'm running the PgCache explain. So you can see that the query is not in the cache. And then we're going to run it. The result comes back. And we're going to highlight as we can see that that query was served as a cache hit, even though we had never seen the query before. I'm going to show a little bit more complicated example. Not very complicated, just a little bit more complicated, just to illustrate that it understands, the where clauses. It could parse uh, the different terms and still compare them. So in this case, we're loading all the actors with IDs between 10 and 20. And then we're just going to select a single row for actor 15. Again, showing that it's not yet in the cache. And then you're going to run the query, and you'll see up here that it'll show up as a cache hit. For the next part of the demo, I'm going to talk about what we call materialized views and memos, memoization. So I've been talking a lot about the principle of caching the data, not the results. As I developed this, I realized, hey, caching the results are pretty useful too. So I ended up caching results after all, because it makes things very fast. So this is going to be initially just showing us a materialized view. As the cache does a little analysis on the queries, and queries that are eligible to be materialized are ones where the resulting row count is, or the result rows is really much less than the source rows needed to compute it. It will also materialize queries that have window functions on the idea that those window functions will be expensive to compute. So using a fairly straightforward example, select count star from a table. This is kind of an extreme example. Count star will return one row. In this case, I've put a million rows into the actor table. So there's a big difference between the rows. We can see it run against origin. It takes about 45 milliseconds. This run was a little bit slower because it caught it during population. A run against the cache before it's materialized. It's 40 milliseconds, and then a run after it's materialized, and we get it back in 2 milliseconds. I'll show you the PgCache explain in a second. And we'll talk a little bit more about what these notices are as part of the explain. We have a line here that says the back end MV for materialized view. This here is the table that is holding this particular materialized view. When I first tried to build this feature, I tried to use Postgres's native materialized views. There are some complications that made that a bit unwieldy, and so this is just a plain table. Yeah, and then the plan still shows you the SQL and the explain as if it had to run the query if against the database if the materialized view wasn't there. But in this case, this is being served from the materialized view. And then the last section of the demo is going to be talking about the memos. So a memo is used for queries that may not be that computationally expensive. In this case, fairly simple queries. And what the memo does is it stores the result set in memory in the proxy. And so if there's a memo available, the proxy doesn't even have to query the internal Postgres database. it could just return the result set from memory, which can be quite fast. So in this case, we have basically simple getting one actor. And you can see the initial query from cache, if it has to do the round trip to the database, is about 5 milliseconds on my machine. When it's memoized, it's down to a quarter of a millisecond. Or a third of a millisecond. And then explain, just so you can see what that looks like. In this case, the back end is source rows, but it marks that in fact it is able to serve from the in-process memoization for the query. So that's it for the recorded demo. I'm going to return back to the slideshow. And for the last section, I'm going to talk about a little bit more about the materialization and memos. Maybe not that much more, because I already described that these were kind of unexpected. When I was talking about earlier about the fact that building with the principle of cache the data, not the results, had paid dividends. These are basically kind of two examples. Once caching the data was working, and it was handling cache hits, and it was handling misses, and it was handling the consistency correctly, working with the CDC stream, and invalidation, these things became, fairly straightforward to build on top of it. And I think covered queries I'm rather excited about. I think it's pretty cool. I think it's kind of unique in terms of what caches can offer. Um, and then finally, just kind of looking ahead in the future, what started off as, how can I just, get this little bit of data I need for authorization onto my edge machines, into my POPs, so that I could do authorization. Asking the question of, if it becomes really easy to spin up a cache, as easy it is to spin up an EC2 machine, in what ways might that affect how people design their system architecture? How can you leverage that? Can you have, not just a few caches in your system, but maybe you have dozens of caches, or maybe even have hundreds or thousands. Basically, from my experience at working at the digital asset management company, the heaviest users were always, a few users, a small percentage of the users were always the most heavy. What if I could spin up caches that are just dedicated to a user? So somebody logs in, I spin up a cache for that session. When the user goes idle or when the user logs out, I could spin down the cache. And what if you could have hundreds of these or thousands of these spinning up? And what if you could do this in the region that's close to the user? I don't know. I think that would be pretty cool. I don't know if it would work, but just kind of looking kind of a long-term, what changes if something that's relatively hard becomes, relatively easy to do. The other one bit to call out is, if you're spinning up 1,000 caches, you're not going to have 1,000 replication slots on your origin machine. So this is basically stealing a page from the ETL, where they use they use some like Kafka or something like that to basically fan out the logical replication stream. So you could essentially have one slot, but you could have many consumers of that slot. So that's what this architecture, or that's what this diagram is trying to illustrate. So, so that's it for my part. I think Philip's going to wrap it up, and then we could get to Q&A.
Yeah, and I'll just do that quickly since we're in the last 15 minutes, I think, here. Thanks, James. So thanks everybody for listening and for showing up and kind of we're really excited now to kind of go to the QA and hear what you guys have to say. Just one note on where PgCache is now. It's so James told me about a month and a half ago. He said, "I'm finally very confident in this product." So that was for the guy who's not building, that's always a great thing to hear. So we're working with a number of people around the world. A couple of them are on this call to kind of test this and benchmark it. We're really excited to just grow that, right? You guys will know a project like this kind of lives and dies on users and on feedback and stuff. So it's live on AWS there's a permanently free, like kind of small server you can deploy. It's not in production yet. I saw your question. I think that's you, Elizabeth. So we're not in production yet, and that's kind of our critical gap at this point. But we believe it's production ready. Obviously, with all the caveats, and you'd want to deploy it on a small workload, monitor and stuff, make sure it's going as planned. So yeah, I was saying we have it on AWS. We've got it. We've got a Docker that's available. You can check out our GitHub repo, and it's source available. So feel free to fork it and play with it and set things up. And yeah, I think I'll pass it on to you guys, Ryan and Elizabeth, for to run the Q&A.
All right. Well, thank you. Yeah, thanks so much for being here. I'll stop the recording.